it's a boost. They might not even tell you you need to use a boost. They will tell you you need to step down the voltage, step up the voltage, or you need to regulate an AC voltage, or so on. So you need to know what does each converter does. So in this example, I told you it's a boost. And you basically are given the voltage at the input, the output voltage that you need to regulate to, and you need to design that. So let's think a little bit about the specifications, and I want to make sure that you guys understand. So you are designing a converter. What is the hardware part that you are going to design for? So you are going to buy a DC source or get a DC source and feed it as an input. And this DC source, you can put it in any value, right? But then your converter is basically starting from here. So you choose an inductance, you choose a MOSFET, you choose a diode, you choose a capacitor, you choose your RCs here. So all of this you choose. So one mistake that I saw in a couple of you, that with all this different specification range that I'm giving, you are changing this L's and C's every time. And in the end, you don't choose one. You cannot do that. You can imagine it. You are building a PCB with the components. How are every time you are gonna change your operating condition, you're gonna take off this capacitor and put another capacitor, take the inductance and put another inductance. You cannot do this. You have to design one converter that fits all, right? So again, what does it mean by fit all? It needs to fit a range. Like imagine you are the customer and you're going to buy a converter, and this converter tells you, I am only gonna work if you put a load of 10 ohms. Will you buy it? No, you will not. I mean, you need a range. You need to make sure that you work a range. And that's how I define those ranges here. So, which I think was a big confusion to a lot of you guys, but this is the range of operation. What can you change? Like, what are the things that you can change? You can change your input, right? Because you have a DC source that you can play with. This DC source, imagine it's like a PV, right? So one time my PV is giving me 12 volts, and one time my PV is giving me 5 volts based on how much the sun is, right? So this will change. So that's why I told you, we have an operation range for this VG, which is basically from 20, sorry, let me just close this. Which is basically from 24 plus 10% and minus 10%. So this is the range that my input voltage can change because of many things, because of like, being a source that have noises around it, because of being connected to something like a PV or an electric vehicle or a grid. So all of this will have different values. So this is the range that my input voltage will change in, and my converter that I design have to handle the minimum and the max and the nominal. The nominal is you're running a 24 volt. The maximum is 24 plus 10. The minimum is 24 minus 10. So this is telling me this is the voltage that I need to run with. What else as a user you can change? You can change your load. You can connect it to a motor. You can connect it to a resistive load. You can connect it to a capacitor. You can connect it to another converter. So your load changes, right? So your load is not something constant. So how does your load change? It depends on power. So that's why we have a range of power here. So what is a load? A load is, it's whatever kind of load. Sphere here, we're just treating it as a resistive load. So you only have active power. So how do you define this R? You define it by the percentage of the power, right? So that's why I gave you the range here from 25 to 250. So you need to design a converter that can work when you have a low power or low load and high load, right? So that are the two ranges here. The one thing that I saw confusing as well, and I don't understand how, this output voltage. This output voltage is given to you plus and minus 1%, right? But what are you doing with those converters? You are creating the output voltage, right? We are controlling our output voltage to be this value, correct? So how, when you are controlling this one, then this is not your mode of operation. You want to make sure that you are staying within. So this 1% is just a safety margin for you to make sure that your voltage stays within this range. So again, if I'm looking at what is my operation scheme, or what is the square of operation for me, I have 4 points. I have my input voltage minimum and maximum. I have my power minimum and maximum, and this defines your operation. This V out is something you are generating. So you're generating this V out to stay within this range. Your best case is when it's equal to 48. But if you remember, we have a little bit of an AC ripple. So it cannot be just 48. It will have to have some ripples. And this ripples is what this 1% define. Why? Because this ripple will be equal to this V out plus delta VO. So those two together, if you add them, will give you this 1% up and down. And that's where this 1% comes in. So again, this is not your design parameters. Your design parameters for the operating scheme, like where are they operating? What is their range of operation? It changes from the voltage and from the load, which is the power. The R of L is directly related to the power, right? Because P is equal to V times I. And V times I, how do you get R? Ohm's law, V is equal to I times R, which means that when I'm changing my power, I'm changing this R of L. So this is the value that you can change, which is R of L. But I have to see. So when we said like here, what are we gonna do? It asks you to do a calculation for all of this. It says all the 4 combinations. Again, what is the 4 combinations? Your 4 combinations is your operating range. Operating range, what can change? Input voltage and output power, which is your load. So if I'm changing this and changing that, I want to make sure that whatever I designed for in the rest of the converter needs to all be satisfying this. So if you have a closed loop, whatever you're going to change in the load or in the voltage, input voltage, you have to still regulate your output voltage to a certain value. So how do you regulate that? It's by changing this duty cycle. And that's why you have 4 duty cycles when we do open loop. We're doing open loop. So there's no controller to make sure that this value stays at 48, right? But I'm gonna change my duty cycle to make sure that I stay at 48. Okay, so this is how this 4 combinations, which I think was confusing you guys, came from. And it was defined for you, VG min, VG max, P out min, P out max, which means it doesn't have any, what? It doesn't have any V out in there. So some of you define those combinations with changing this V out plus and minus. It doesn't have the V out. It's given to you as voltage, minimum voltage and maximum voltage of your input voltage, and then minimum output power and maximum output power. So those are your 4 combinations that you have. So I wanted to go through this just to make sure that you guys understand the concept, and then we're going to go through the solution and go each part, what does it mean.
Yeah.
Do you have questions
I'm going to need this
up here?
recorded for when I do the final project. And I can try and take notes, but recording's 100 times better.
That's okay.
Any questions? Okay. So if no questions after hearing, so let's go through the solution and see what are we required to do. So this project had 2 parts. Your first part is you needed to do all the calculations for those things that are being asked here, and we're going to go one by one. And then after you do that, basically by doing this worst case scenarios, you are choosing what should be my circuit. So I'm going to have 1 circuit. So I'm going to have 1 inductance, 1 capacitance, 1 MOSFET, 1 diode. The only changes that's going to happen afterwards when I'm doing my simulation is I'm going to run the different cases for input voltage and output load, which is the power, and I'm going to put the duty cycle corresponding to this one based on what I calculated. So if we go here to the solution, and again, let me just go because I want you also to look at the report. So the last page in the project asks you how you want to have your report. So it was very simple. I told you I want a cover page. This cover page has the course number, course name, project title, your name, your student ID, the date completed, and a statement. So again, there's points on this, and it's very simple to have. I asked for an abstract, I asked for an introduction, and I told you what to put in each and every section. And also this design and verification, this design approach is all your equations. Here I say design process, equations, steps, and then all the results like being in tables or put in a way that you can read it. And then simulation verification, which is all your waveforms, right? So again, it told you that you're gonna have 70 points on your technical and 30 points on your structure here. And again, this is how your Excel sheets, you're gonna see like there's 2 parts. 1 part is on the technical part and 1 part is on the structure. So So here, I'm gonna actually, this is my cover page. Again, it's just have a number of the class, Power Electronics, Project 1, name of it, name of the student, student ID, and then whatever the date you submitted in, and then just saying that you submitted this by yourself. See here, we're having like a table of contents, which basically your Word file is gonna generate for you. So after you're done writing everything, then you just say, create this table of contents, and it will create that one. So this one, we started with an abstract, introduction, specifications, design, and then how you went through all of the design, all the steps that were asked for, and then simulation verification, and the results of it. And this one have, actually, this solution have a little bit more than what I asked you for, so we're gonna skip when we reach that stage. So the abstract here, I just put like a small paragraph saying what we do. So what are we trying to do? We are doing a power stage design for a boost converter. How did you approach that? First, the duty cycle was calculated for the 4 combinations. Then the combinations again is what? The different input voltage, VG, and output power. And then after this, we calculated for the current to make sure, and this is important, because when we talk about the current, I'll tell you this. It said continuous current mode. So you need, sorry, this is wrong, continuous conduction mode. So if you see here in the problem, I mean, each and every sentence meant something. So you had to read it very carefully to be able to solve everything. It said the converter should operate in continuous conduction mode. So, and the ripple specifications must be under the all operating conditions. So you need to make sure that your ripple will fit all the cases and that your system is running in continuous conduction mode, and that will be affecting your inductor choices. And we're gonna see this next. So then it tells you if you're running with this continuous conduction mode, then you need to choose a proper L. And after that, you choose your capacitance, then you calculate for all the worst case values. And then from there, you can actually select your power stage component and go ahead and demonstrate it, whether in Spice or MATLAB, whatever you choose. And then finally, a summary of the thing. So your abstract, what does it do? It tells you what you're gonna see. So it's a small thing that tells you what is the problem you're trying to solve, how did you solve it, and what is the results, the main results that you get. And again, this is important for, especially for people who are gonna go and do like, graduate studies, but also if you're working in industry, they require you to write reports for your projects. So you need to put it in something similar to this. And I think it's a good time for you to learn that because you're mostly all seniors and all graduating. So, again, the introduction, I just stated very little that we are required to design X and Y and Z, and this is the components that, and then the specifications are shown below. Specifications comes directly from your paper. So what is the paper? It's what I understood when I read that. So this is my boost converter. My specifications is I need my voltage, input voltage to stay between 24 plus and minus 10%, my output voltage to be 48 plus and minus 1%, my output power to work for 25 to 250, and then my ripple for output voltage is less than 50 millivolts, and switching frequency is given as 200 kilohertz. So this is all from the problem, so I didn't really put anything now here.
We slacked on the Wii Fit.
So,
we're gonna do it today.
again, just to simplify for myself, then I translated whatever those things means into the numbers. So VG, the percentage of it as max and min, this is basically what it is. And then the power output, again, maximum and minimum values. And then from the switching frequency, I can get also my period, which I would need. So with that being said, I put all the specifications up to here. From here starts my real work. So my design approach. So again, I'm just kind of repeating myself here. I'm just saying what I'm gonna do and what I'm gonna calculate for. So I'm gonna skip this part and I'm gonna go through the design process for you. So what is the first step? It's the same DC analysis we used to do. So what is the DC analysis we used to do? We have two equivalent circuits, subinterval 1 when you're connected to the MOSFET and subinterval 2 when you're connected to the diode. You need to write each and every one of them, and then you need to write your equations. So steady state analysis. To be able to calculate your duty cycle, which is the first requirement, I need my steady state analysis. So what do? We write two equations, one for the inductance, the KVL, voltage across the inductor, and one for the capacitor, which is the KCL. And then that's during your on time, during your off time. those two equations, what do I do is, if I want to get my duty cycle, I need to do inductor volt second, which means the average of the inductor voltage should be 0. Let me hide this one. It should be 0, right? So I'm combining those equations, equation when the MOSFET is on and when the MOSFET is off. This multiplies by dTs and this multiplies by d prime T of S, and we equate it to 0. So this, we do that. And then my second equation that will get me the inductor current is the capacitor current. The average of the capacitor current for one cycle is equal to 0, which means I have equations number 2 and equation number 4 here. This one multiplies by dTs and this multiplies by d prime T of S. And then from those two, I can get what is I of L. Okay? So again, you see how the formatting is? I'm writing each equation, I'm numbering the equations, and it's clear and easy to follow and read. Helping you and helping us as well, and also learning how to write a report. So once you do that, then you basically get two things. You get this I of L, and you get an equation. And most of you, if you don't really simplify too much, you're going to end up with a quadratic equation like I did here for z prime. And you solve this quadratic equation, and you can use your calculators for that, just defining it with the standard quadratic equation, which is here. D prime will be equal to minus b plus and minus square root of p squared minus 4ac over 2a. Whereas those values are, those are the coefficients of the equation. So a is what's multiplied by d prime squared, b is what's multiplied by d prime, and then c is your last term. You solve for this one, and you're gonna get for each case, we're gonna substitute for each case. You have 4 cases. So what are your cases again? Your minimum input voltage with minimum output power. Your minimum input voltage with maximum output power. Your maximum voltage with the minimum power, and your maximum voltage with the maximum power. So this is giving you the 4 cases. And as you can see here, you have 2 values. A value that's about 0.5 or 0.4 to 0.6, and a value that's very, very small. So this value that's very, very small for D prime means what? It means D will be on all the time. Can you do that? Is that possible? If the duty cycle is always on, then you're just short-circuiting the circuit. You're not really going into sub-interval 2. So you have to, when you find those 2 numbers, you have to choose this value and ignore or actually neglect the other one. And that's how you have it. So you neglect the smaller values, you have those 4 ones, and then this is the first part, which if we go back here, this is the first calculation it asked us for. So this is the steady state duty cycles for all the 4 combinations. I'll stop here for a minute and make sure that you guys are following. Any questions?